All right, welcome back. This is going to be, I believe, the third video for Unit 6 for AP Environmental Science. In this video, we're actually going to do 6.4 and 6.5. 6.4 is very quick because 6.4 is all about the distribution of natural energy resources. What's important to understand about the distribution of natural energy resources is it's not uniform, and it very highly depends on what your geological history is of a region. So basically, we don't have coal everywhere, and we don't have gas everywhere, and certain places have more and certain places have less. And so it's very dependent upon the geologic history to know how much fuel is in an area. Now, as we go through all of the different energy sources, there are going to be a few times where we're going to have a map to show you where you can find the majority of these resources. I'm going to give you the map in class so that you can use it. So when we get to these sources, you're going to want to color in or label the map with the different energy resources. So make sure you're doing that as you either watch these videos or if we do notes in class. So that is the end of 6.4. We're now going to move in to fossil fuels, which is, the majority of our energy. This is a fun one. I love this little image. It's always the idea, dinosaurs really just existed to create oil. We can then use oil to create plastic, and then we finally can turn plastic into little plastic dinosaurs. So it's kind of full circle. We're taking dinosaurs to make dinosaurs. Now, what are fossil fuels? Fossil fuels are a non-renewable resource that were created from biologic material that was fossilized millions of years ago. For the most part, 50 to 350 million years ago. They were formed in anaerobic conditions like swamps where there is no oxygen available. So this gives you an idea of the fossil fuel formation with coal versus oil and gas. Coal, you can see here, we had huge forests that were growing on land. The vegetation then dies and formed peat. The peat was then compressed to form lignite. Further compression formed the bituminous coal, which, if you recall, is the most common source of coal. And then over enough time, with enough pressure and heat, you could eventually get anthracite. Oil, on the other hand, for the most part, is produced because of marine plants and animals that died and sunk to the bottom of the seabed. The plant and the animal layers were then covered with mud, and then over time more sediment compressed that matter with more compressing those into an oil. And eventually the oil would move up in through the porous rocks and eventually form reservoirs. And so you can get an idea that we mine for the most part when it comes to coal, and you see a lot of oil rigs in the ocean. So this just shows you the idea of oil versus gas and their formations. For the most part, coal is formed from forests that were on land and eventually compressed after they died, and oil and gas were more formed from marine life that was then compressed underneath the ocean in the huge amount of pressure of the ocean water along with the sedimentation. Now, when we talk about combusting fossil fuels, we look at complete combustion versus incomplete combustion. And the reason for that is because it's important to know the difference, right? If you have complete combustion, you're not going to have as much pollution. If you do have incomplete combustion, there is much more pollution. So if you recall from chemistry, we get a hydrocarbon combined with oxygen through combustion to produce carbon dioxide and water. For an example, cellular respiration is combustion. A glucose is combined with oxygen to produce carbon dioxide and water. Of course, the other product that we don't show in these equations is the energy that we're trying to get. So we burn fuels to make energy. We have combustion, which makes heat by burning fuels in one step. We just burn it. Aerobic respiration is a little bit different. It still is combustion, but this is where you create ATP and a little bit of heat by burning fuels in many small steps. This is the process that your body goes through to produce your energy versus the combustion of organic material to produce our electrical energy or heat energy. Now the difference, another big difference between cellular respiration and combustion is that cellular respiration is very slow, it's very controlled, your body does it in a very, very, very specific way. It regulates your body temperature, it occurs in living cells, and the energy is released in different steps, which is then stored in your ATP. Combustion, on the other hand, is very quick. There are huge high temperatures. It can be done anywhere. It doesn't have to be in a living cell. And the energy is released in the single step in the form of heat and light. So incomplete combustion is a little bit different. And the reason that incomplete combustion is so important is because if you do not get enough oxygen available, incomplete combustion will produce other products. For instance, carbon dioxide. So if there's not enough oxygen, you get leftover carbon, which would then be released as soot and carbon monoxide, which of course are not great for the environment. So in this example, this picture here, if you guys remember using a Bunsen burner, as you open the air, you get a more complete combustion, and you're actually producing less of the waste products. When you leave the air, the oxygen valve closed, you get a much weaker flame, and you actually are producing a darker smoke typically because you are producing soot and carbon monoxide. So complete combustion requires sufficient oxygen. It's going to produce carbon dioxide and water. You usually get a blue flame, there's no smoke, you get a lot of energy, but of course the CO2 does in fact cause global warming. So it's important to understand that just because it's cleaner and complete doesn't mean it's great. Incomplete combustion just means there's not enough oxygen, so you end up getting carbon monoxide and water. You usually have a yellow or orange flame and a lot of smoke or soot. Now, you don't get nearly as much energy produced in this form, and the carbon monoxide and smoke causes air pollution, which can also lead to lung disease. So there's a very big difference between complete combustion versus incomplete combustion. And the big thing that's important for us to understand is if we're using combustion to produce energy, we want to make it as complete as possible. Alright, so let's look at some of these fossil fuels. And the first one we're going to look at is coal. Coal is the most abundant and the dirtiest of all the fossil fuels. So if you recall from way back, it's just the remains of trees and other plants that were preserved from millions and millions of years ago. This is still the most common use of energy, or the most common fuel for energy in the United States. And it's very ideal for stationary combustion applications like power plants. We don't typically use it for moving vehicles. Now, of course, in the days of the steam engine, coal was in fact used as a source for non-stationary and moving applications, but now we've kind of moved into a day of using gasoline for that, so we don't use coal in a moving vehicle. The way a coal-burning power plant works is the coal comes in. The coal then goes into the boiler or the furnace where it is burned, and water is pumped through and heated as it goes through that process. So the water comes in fairly cold and is heated with the heat generated from the burning of the coal. That water, because it turns into steam, has higher pressure, and the steam then enters into a turbine where it spins this turbine really, really fast. As it does that, it actually transfers its energy into the turbine and then loses energy, which gets it back down into the form of water. It goes into a condenser, which uses cold water, typically from a river or some water source. The cold water actually helps to cool that water, bring it back down into a colder form of water where it can then again be pumped back in and used again to power the steam engine. So the turbine spins, which generates electricity through the process of using magnets. It's the basic way. You spin a magnet around and you will generate electricity, and that electricity then can be sent out, transformed, and transmitted. So the coal mined and transported, burned in the boil, the energy is transferred to the water steam turns the turbine turns the generator, and it's very important to remember all of the water that is used in this process, all of the emissions that are coming out of this process, because the emissions have to go somewhere. So here are the emissions that have occurred since 1751. What percentage of global fossil fuel emissions have occurred in your lifetime? Well, if you're 5, only about a little over 10% of the world's emissions. Now for you guys are about 15 in this range right here, right? 15 to 20. In your lifetime, when we're looking at just global fossil fuel emissions since 1751, when we were really starting to produce energy using fossil fuels, about between 30 and 35% of all of the fuel emissions have occurred in your lifetime. A third of the fossil fuel emissions in our atmosphere have been emitted in your lifetime. For me, I'm about 30. It's over 50%. Notice as we go, this actually starts to fall down. And the reason for that is because in the last 30 years, we have doubled our emissions from the previous, since 1751. What is that? 240 years? We produced in the last 30 years the same emissions, or actually more emissions, than the previous 240 years combined. Remember the coal? We talked about coal in our last unit, so we're not going to go into too much depth here. Just remember the 3 types of coal: lignite, bituminous coal, and anthracite. Here are the major coal deposits in the world. Anthracite and bituminous coal is going to be in the orange-red. Lignite, which if you recall, looking back here, is the less useful form of coal, is going to be found in green. I would pause the video right now and label your map a little bit, figure out how you want to do it. But you can see we have a lot of sources of coal in the United States, huge sources in Russia, throughout Asia, a little bit in Europe, very little in South America, almost nothing in Africa, a good source in Australia. Notice there's some good coal in northern Alaska. These are all the sources that you're going to find coal. So I'd pause the video here, label your map. I don't think I gave you guys the map before you watch this video, so I apologize. And if I did not, and you don't have your map, come back to this and make sure you label this at some point. Just in the United States, we're looking at our coal sources. You're going to remember anthracite and semi-anthracite. These are going to be in the green. Very little. Right? A little bit in Washington. Low volatile bituminous coal, and then medium and high volatile bituminous are going to be in red and yellow. Notice the medium and high volatile is very common in the Midwest and in the East. A lot of lignite up in North Dakota. And that's because typically you find a lot of lignite near oil reserves too. And this just happens to be an area where we found a huge amount of oil reserves. Sub-bituminous coal, meaning not quite good enough to be used, still can be used for smaller applications. That's found throughout the West. I guess this is technically part of the West. And then, like we said, the lignite here. But you notice these bands. So these are areas where you're going to find a lot of coal and a lot of coal mining and a lot of coal generation. Now, some of the advantages to using coal is that there are abundant reserves compared to oil and gas. So these are just some of the numbers. 46 million barrels of oil are pumped today. It's estimated that we have about 1.5 trillion barrels of oil left. So we have about 44 years until we use the rest of the oil, assuming that we keep pumping at the same rate as today. Natural gas, on the other hand, the amount of natural gas used or available is a little bit less. There's about 1 trillion. But we don't have to use as much, so we have about 57,000 days left of natural gas. You can kind of do the math there. It's about, 4 times as much, so about what would 4 times? About 200 years-ish, give or take, a little less than that. Coal, on the other hand, oh, we have about 4 trillion barrels version, right? This we're looking at the equivalent of a barrel of oil, so that's what BOE is, barrel oil equivalent. About 4 trillion. So we actually have 149,041 days to the end of the amount of coal that we have. We have a lot more coal. We have about 119 years left of coal. Man, I did the math wrong. 63 years of gas. I was saying 200. I guess, oh yeah, because we use it in a different way and it's not as efficient. So there's a lot more coal available. So we don't have to really worry too much. And that's a big part of it. So we can say we're going to have coal for a long time, but are we going to have coal forever? Some more advantages, of course, is that it's easy to extract. You can surface mine it. There's not a whole lot of technology involved in this process. Dig a hole, extract the coal, doesn't cost much. It's also very safe to store. You can just put it in storage. It can be stored for future needs. It's not the type of thing that we have to use immediately. Natural gas is much more difficult to store. It's pretty easy to transport. You don't have to have pipelines. You don't have to worry about a coal spill. You can just put it on a train. And you don't really have that much work in refining it. Coal is almost perfectly useful as it is mined. Of course, disadvantages do exist. The disadvantage just from surface mining, we have tailings that contaminate the waterways. So oil sands study confirmed tailings found in groundwater in the river. This was in 2014. As these chemicals and waste products are contaminating our groundwater and our river water, our fresh water becomes less useful. Coal is also the most dirty form of energy production because of the air pollution. When it's burned, there is sulfur, mercury, lead, and arsenic released in sulfur dioxide and airborne particulates. Coal is about 60 to 80% carbon, so most of it's converted into carbon dioxide, which of course contributes to atmospheric increases. So just the carbon content, it has the most carbon content compared to oil and natural gas. There's also residual ash, which is about 3 to 20% that remains behind after it's burned, because there has to be something left behind. And there was a huge ash water spill in Knoxville, and it took about 5 years and about $1 billion to clean up afterward because of how toxic and dirty it was. In that ash, there are heavy metals and radioactive material. Now, petroleum, we're going to move on to, also known as oil, is cleaner than coal. Doesn't mean it's clean, just cleaner than coal. Petroleum is just a fluid mixture of hydrocarbons, water, and sulfur, and it occurs in underground deposits. Now, what's nice about it being a fluid is they're more suitable for mobile combustion like vehicles. Petroleum was formed by the phytoplankton algae remains, remember, in the ocean. Porous rocks are covered by non-porous, and over geologic time, the algal remains will then fill in those pores to form the petroleum. It's less dense than rock, so as the rock deforms, it migrates closer to the surface, and then it can eventually be drilled and extracted, and then we can use supertankers or pipelines to take them to refinery, to take the petroleum to refineries to turn it into more useful products. So crude oil is just liquid petroleum that's directly removed from the ground. The natural gas is burned off or extracted for separate fuel. There is natural gas with crude oil. Crude oil can be refined into tar and asphalt. It can also be refined into gasoline, diesel, and kerosene. Each of those depend on the temperature at which they boil. So they change. You can extract them based on the temperature at which they boil. So this is the process of distillation of crude oil. Crude oil is put into a boiler to be heated, and we can actually use, as you see, we get the gas that we're able to get from our crude oil here. So based on the temperature, all the way from 600 degrees Celsius down to 20 degrees Celsius, different byproducts of the crude oil are able to be taken out. That's not important. It's not super important that you understand each of these processes. Just understand that crude oil is then turned into all of these different sources. Gas is the lowest in temperature byproduct. Gas, not gasoline. This would be like natural gas. Oil refining, of course, is very complex. I mean, this is a very broken down and easy version of oil refining. This is what a real oil refinery looks like. It's complex, it's dangerous because of the high temperatures involved, and it requires a huge amount of investment. There's a lot of money. A barrel of oil will give you about 42 gallons total of oil. That's what a barrel is equal to. So where's oil? This is another one of those label your map moments. The proven reserves in billions of barrels, and proven meaning that there actually is proven a number of barrels. We can prove it. It's not just an estimated number. In the top 20 countries in 2006, 1,224.5 barrels were located in the top 20. The rest of the world had 68.1. So it's really important to remember that the resources are not uniform and exist in different areas. Canada has a huge amount of oil reserves, and that is actually something that has helped the United States because we have not a huge reserve, but we are able to import a lot of oil from Canada. Saudi Arabia has the highest. Now this is why right here, this is the zoom in of the Middle East, and this is why the Middle East is so highly contested, because most of the oil reserves in the world exist in the Middle East. Venezuela is also a hot topic when we talk about oil reserves. But you can see here all of the different places. The circle size gives you an idea of the relative amount of oil in that country. So make sure to pause here and write down or label on your map oil and the locations of these majority of the oil left. Now this is Alberta's boreal forest. So this is Alberta, the boreal forest here. You can see the oil sand deposits. This is why we talk about tar sands and oil sands in Canada. There's a lot of it. You can see up here, this is where you have oil sands that are mineable and then have already been mined is the tan, and the red is where it's going to be easily surface mined. The rest of the deposits, of course, they will have to work on how to get it, but this is where a lot of that oil is coming from now for the United States. Some of the advantages of oil and petroleum. Liquids are convenient to transport, again, so we can use it for combustion engines. If you don't know how a combustion engine works, essentially you have induction, which is where the fuel and air come in. Fuel comes in through one valve, air comes in through another. Then it's compressed to create a higher compression. Then it's ignited and given power. The fuel burns under that high compression, which then moves this piston fast, and then finally the piston moves back up and exhausts the whatever the exhaust is, the carbon dioxide, the water, any of the byproducts. So this whole process is spinning the crankshaft, which eventually runs your engine, moves your engine. Now compared to coal, it's very energy dense and cleaner burning. 85% of the carbon dioxide that coal does is burned with petroleum. So it's not nearly as much carbon dioxide compared to coal. Some of the disadvantages, of course, there is sulfur released into the atmosphere and trace metals like mercury, lead, and arsenic. There are potential for leaks and oil spills. You hear about them all the time, I'm sure. There's also a huge amount of habitat destruction with pipelines and oil well constructions. So this is the Keystone XL proposed route, and these are the whooping cranes and their migratory route. And the reason that a lot of people were worried about this as being a habitat destruction. There are also gas flares that have to be done to keep volatiles from getting too dangerous. Some of those, I'm going to give you some of the issues. In 1989, the Exxon Valdez oil spill occurred where a supertanker crashed into a reef in Prince William Sound, Alaska. 42 million liters or 11 million gallons of oil was released, and 500,000 birds and thousands of marine mammals were killed. Now, the Arctic National Wildlife Refuge is an area that, if you recall from our beautiful picture earlier, this is actually where some oil is being mined. It's believed that exploration could yield between 1 and 1.4 trillion liters of oil and natural gas, and the opponents are saying that it will harm the pristine habitat and the human population in this area. Another example of a disaster that occurred was Deepwater Horizon, and it was an explosion at a British petroleum oil rig in the Gulf of Mexico. 780 million liters of oil was released over 87 days. 6,000 sea turtles, 26,000 marine mammals, and 82,000 birds were killed in this process. That's going to bring us to natural gas, our next fossil fuel. So natural gas is the cleanest of the three fuels, and it exists as a component of petroleum in the ground as well as in gaseous deposits found separately. For the most part, it is methane. The rest is ethane, propane, and butane. And it's lighter than oil, so it actually lies above oil in deposits. So typically when you find oil, you'll find natural gas. Natural gas can be used residentially, commercially, industrially, for electricity, and for transportation. Industrial processes, it can be used for electricity generation and residential heating. So this just shows you where the natural gas is being used. For the most part, it's electric power. A pretty big component is used industrially, then commercially and residentially. None for vehicle fuel. Now it's 0%. You actually can find a few vehicles that will run on natural gas. They're just not very common. Now some of the advantages is it doesn't have as many impurities. It emits almost no sulfur dioxide or particulates during its combustion, and 60% of the carbon dioxide is released as compared to coal. It's also easy to deliver through pipelines, and there's not as much of a risk. The problem, of course, is it's very light, and if it is released, it will create more global warming. So some of the disadvantages is that, like I said, that natural gas in itself is a greenhouse gas, and it's 25 times more efficient at absorbing energy in the atmosphere than carbon dioxide. So in the short term, it's 84 times more potent. It's a much, much, much worse greenhouse gas than carbon dioxide. Now this just shows you per human, because humans do produce natural gas, methane. Looking at humans, we produce per year 0.12 kilograms versus, a Western cow produces 120 kilograms. So you can get an idea of methane that's produced from different animals. Now how we're getting it is through fracking, which is hydraulic fracturing. Now, one of the risks that comes with hydraulic fracturing is we can contaminate the groundwater, and there are possible chemicals that are toxic being released into groundwater through the process of extraction. So this is how fracking works. The shale gas extraction, you have a well that sends down water, sand, and chemicals that injected down deep below to create fissures to then release the gas as it comes back out the other way. Where the risk is that you have to go through the water table to get down there, and the chemicals that are being used can be released eventually in these fissures into the water. So again, looking at this, we have the fracking fluid forced underground at high pressure to break apart these rocks and release the natural gas. but those chemicals that are pumped down there can be seeped into the drinking water, which then seep into the aquifers and are contaminating the systems in the drinking water systems. So let's look at some of the methods of oil extraction. There's onshore and offshore drilling. For coal extraction, you have underground and surface mining. And for natural gas, there's traditional drilling and separation from oil, but there's also fracking, which is shale gas. As far as energy intensity, we're looking at the energy use per unit of GDP, the gross domestic product, essentially meaning if it is giving you, when we're looking at energy intensity, do you get a lot of energy versus the money that goes into it? Some of the influencing factors like economic production. The lower the EI, the more efficient it is. In a rich country, the economic production is going to be high. It's going to be very low if there's a higher EI. The economic production will be very low if there's a higher energy intensity. As far as weather goes, if it's mild or moderate, you're going to have more efficient. If it's very cold or very hot, your energy intensity is going to be higher because you're going to have to use more of it. As far as mass transport goes, if there's an extensive system and it's widely used, you're going to have a lower energy intensity. If there's not much available, you'll have a higher energy intensity. And these just give you a few more. It's pretty basic and pretty straightforward. You're going to have more efficiency depending on what you've got. If you have shorter distances to commute, if the fuel economy is high, if the size of the area that you live is small, these are all possible ways to make more energy intensity, to have less energy intensity. So when we look at tons of oil equivalent per $1 million, this shows you the countries that are using it the most per the money that the country has. The United States right there above the world average. So what does it mean when we say that the United States has near world average energy efficiency? It means that we are using energy more efficiently, but because we have a high population and we have a growing number of population and we have more ways that we use energy, our overall energy use has not decreased. We're using more and more energy even though we're getting more efficient technologies. That brings us into looking at production. It's Hubbard's peak oil production. His belief is that there's a point at which your production is going to hit its maximum, the peak oil, and then you will start to find supply going and being used up. So oil use, it's used to project when oil production will reach a maximum and when it will be depleted. His belief was that in 2000 the peak oil production would exist or happen. There are other models that say that we reached it before 2000. And William McDonough, this is a fun quote, "The Stone Age didn't end because we ran out of stones." So hopefully the fossil fuel age will not end because we run out of fossil fuels. So that brings us to the end of 6.5. The next video in the next section of notes will be 6.6, nuclear energy resources.